3.4 Concavity. In previous videos, we learned how to use the derivative of a function to find extreme values, helping us graph functions. Now we can use a second derivative to learn about the concavity of a function. Concavity is the curvature of a graph, and it can go either up or down. Concave up looks like this, and concave down looks like this. Concave up graphs open upward and concave down graphs open downward. If you think about it, concavity involves how fast a graph is increasing. As a result, we can use the second derivative, one step up from the first derivative, to identify concavity of a graph at a certain interval. The process is similar to the one we used to find extrema, except you'd use the second derivative instead of the first. Here are the steps. Step 1, take the derivative of the function f. Step 2, take the derivative a second time. And now, step 3, set the second derivative f double prime equal to 0 to find x values, called points of inflection, similar to critical values except for concavity. Step 4 uses sign chart, but this time testing values in f double prime, to find points of inflection and concavity. Let's try an example. We are given a function and asked about its relative extrema and points of inflection. Our first step is to take the derivative. We get that f prime of x equals 4x cubed minus 12x squared. When setting that equal to 0, we get 0 equals 4x squared times x minus 3 to obtain critical values of x equals 0 and x equals 3. Now, we must take the derivative again. This time, we obtain f double prime of x equals 12x squared minus 24x. We can extract a 12x from this to obtain 0 equals 12x times x minus 2. Therefore, we get points of inflection of x equals 0 and x equals 2. Now, let's create a sign chart using both the critical values and points of inflection, but splitting them only where the first and second derivatives have critical points. The first derivative is on top and the second derivative is on the bottom. When I tested each of the values in the intervals, I got these signs: negative, negative, positive for f prime, and positive and negative, and then positive for f double prime. This tells me increasing, decreasing, and concavity. Therefore, I now know that there is a maximum at x equals 0. There is a minimum at x equals 3, and there are points of inflection at x equals 0 and x equals 2. To clarify, we know that x equals 0 is a maximum because the graph goes from increasing to decreasing, and that x equals 3 is a minimum because the graph goes from decreasing to increasing. To determine concavity, we know that it's concave up from the interval negative infinity 0 and in the interval from 2 to infinity. We also know that it's concave down when f double prime is negative, meaning on the interval from 0 to 2. In this example, we must find the extrema, points of inflection, increasing and decreasing intervals, and concavity of this function. We must use the same process as before. First, take the derivative, this time by using the quotient rule. In this case, f prime of x equals low times the derivative of the higher function minus high times the derivative of the lower function, all over the lower function squared. And that's our derivative. To simplify, we can set it equal to 0 and get that 0 equals 4x squared minus 2x minus 2x squared, and we can leave the expression on the bottom. Now, to further simplify, we can say that 0 equals 4x squared, I meant 2x squared minus 2x all over 2x minus 1 squared. That can be simplified into 0 equals 2x times x minus 1 all over 2x minus 1 squared. This gives us critical values of x equals 0, x equals 1, and looking at where the function does not exist, x equals 1/2. Now we must take the derivative yet again to find points of inflection. In this case, we must use the quotient rule again. F double prime of x equals low 2x minus 1 squared, d high, which is 4x minus 2, minus high 2x squared minus 2x, d low. We must use the chain rule. Bring the power down, subtract the power by 1, and multiply by the derivative, and all of this must be divided by the square of 2x minus 1 squared, giving us 2x minus 1 to the 4th power. Now, if we simplify that, we get that 0 is equal to 4x minus 2 all over 2x minus 1 to the 4th. Therefore, we get that the points of inflection are at x equals 1/2. Now, I must use a sign chart to find where the graph is increasing, decreasing, concave up, and concave down. When I plugged in values into both f prime and f double prime, I got that for f double prime, the graph goes from negative to positive, and then for f prime, it goes from positive to negative to negative to positive. This tells me that the graph is increasing, then decreasing, decreasing some more, and then finally increasing. And then the graph is also concave down and then concave up. This tells me that there is a maximum at x equals 0, where the graph goes from increasing to decreasing. There's a minimum at x equals 1, where the graph goes from decreasing to increasing, and there is a plateau at x equals 1/2, where the graph does not change signs. The graph is increasing at x from negative infinity to 0 and from 1 to infinity, and the graph is decreasing from 0 to 1/2 and then from 1/2 to 1. Finally, with the second derivative, we can say that the graph is concave down from negative infinity to 1/2, and we can say that the graph is concave up from 1/2 to infinity. And that is our answer. Moving on, the second derivative test is another test for extrema, and it states that if f prime at some value c equals 0, and f prime of x exists on an open interval containing c, then if f prime at c is positive, f of c is a relative minimum. If f prime at c is negative, f of c is a relative maximum, and if it equals 0, there is no conclusion. Looking at the concavity of the graphs, if the graph is concave up, there must be a relative minimum, while if a graph is concave down, we can see that there must be a relative maximum. Let's try an example. In this case, we must find the extrema of a function f of x equals 5 plus 3x squared minus x cubed. First, we have to find f prime of x, then set it equal to 0 to find critical values. So in this case, f prime of x equals, well, the 5 disappears because it's a constant, so all we have to do is move the power down and reduce it by 1, giving us 6x minus 3x squared. So let's set that equal to 0, and then extract a 3x from the 6x minus 3x squared, giving us 0 equals 3x times 2 minus x. Therefore, we know that the critical values must be at x equals 0 and x equals 2. Now that we have our critical values, all we have to do is use the second derivative test. So to do that, we must take the second derivative. So all we have to do is take the derivative again of the f prime of x function. In this case, f double prime of x is equal to simply 6 minus 6x. So let's plug that into both x equals 0 and x equals 2. F double prime at 0 is equal to 6 minus 0 equals 6, while f double prime at 2 is equal to 6 minus 12, which makes it negative 6. So since f double prime at 0 is positive, that must mean that there must be a relative minimum at that point, since the graph is concave up. And since f double prime of 2 is negative, there must be a relative maximum at that point, because the graph is concave down. And that is our answer. Thanks for watching.